Okay, let us study the control integral representation of the theta function. Theta function appears in the time-ordered product, and if you make use of this relation, it is very easy to generalize the higher order fraction to the time-dependent perturbation field. So, let us first write down the answer. Theta function is 1 for positive t, and it's 0 for negative t. And it can be defined to be limit as epsilon goes to 0 plus, very small number, but it is a positive, I over 2 pi, integral over the omega, from minus infinity to plus infinity. We have numerator in the integrand, exponential minus I omega t. In the denominator, we have omega plus I epsilon. If you replace this omega by energy, by making use of the fact that energy is h bar omega, we can change the variable like that. So this can be, this relation can be proved by making use of control integral. Let us define the control integral I, which is the same as the over factor is the same, and integrand is the same. But this contour, depending on the integral, depends on the contour, whether it has residue inside the closed contour or not. We define two contours. C plus runs from minus infinity to plus infinity, and it is closed along the upper half plane. And C minus is the contour that is along the real axis. Both of them are running from minus infinity to infinity, and the contour is closed on the lower half plane. So, in short, C plus integral is real axis integral from minus infinity to infinity plus this semicircle, as the radius r goes to infinity. Minus r to r, and take the limit as r goes to infinity. Then we find that this C plus control integral is 0. And the residue of this integrand is at omega is equal to minus I epsilon. So that residue can be found by replacing omega by minus I epsilon here. So we have exponential minus epsilon t will be the residue. So if we close the contour along the lower half plane, that control integral is non-vanishing. The upper half plane, this contour integral is 0, and non-zero value can be found when we close the contour in the lower half plane. So as I already told you, the residue of this integral is the value I, we have over factor I over 2 pi, I over 2 pi, and we have exponential minus I omega t in the numerator, and we put omega is minus I epsilon here. Then the value is I over 2 pi exponential minus epsilon t. As epsilon plus, epsilon goes to 0 plus, this guy becomes 1, and the residue is I over 2 pi. So the plus contour, C plus contour integral is 0, as I already told you that if this integral does not have a residue. And c minus integral has the residue whose value is I over 2 pi. And we recall that this contour is closed along the clockwise direction. So we put minus 2 pi I. Okay? So if I multiply minus 2 pi I, then the whole integral becomes just 1. So in short, this integral is 1 in any case, and this integral is 0 in any case. Okay? But this theta function is expressed as an integral from minus infinity to plus infinity. So this integral is not exactly the same as those contour integrals. They are the same as this integral only if this integral on the semicircle vanishes. So we'd like to see whether those integral vanishes or not. And actually it depends on the value, the sign of the time t. Let us first close the contour, the lower half plane, and those integral, that integral, absolute value of that integral, except for this over factor, can be written like that. Okay? So I would like to evaluate the magnitude, the absolute value of that integral. On the lower half plane, omega can be parameterized by omega equals r times exponential minus I theta, where theta goes to 0 to pi. Because I put negative sign in here, theta runs from 0 to pi. So if I evaluate the d omega, what I get is minus I r exponential minus I theta. So that is the same as minus I omega d theta. Okay? So if I consider this factor omega, and in the denominator we have omega plus I epsilon. I epsilon is necessary in the denominator only if there is no omega here in the numerator, because when omega becomes 0, it is not defined. So without this I epsilon, this integrand is not defined along the real axis. But because of this I epsilon, the denominator is always defined along the real axis. But in here, along the large circle on the lower half plane, omega is like that, and that omega cancels omega plus I epsilon, exactly. And actually, on this circle, omega is not 0 always, so this I epsilon is not necessary really. So, because of this omega in the numerator, we can cancel down those factors. And I'm interested in the size, the magnitude of this integral. So from this fact that omega theta runs from 0 to pi, I have replaced that d omega, the complex integral, as just a real integral. Integral over a real number, that is angle, from 0 to pi. And we have substituted the value of omega in the numerator. That is exponential minus I r exponential minus I theta. That is a cosine minus I sine theta. And I put t. Alright. The value of this integral, absolute value of this integral, is always less than the integral of the absolute value of this integral. Okay? This is generalized Schwarz inequality. So in that case, oscillating factor disappears if I take the magnitude, absolute value of the integrand. What I have is minus I. So minus r t sine theta is the only contributing useful contribution in the absolute value. So we would like to evaluate that integral, but actually what we want to find is the integral along this path, and actually vanishes or not. We would like to see whether this integral vanishes or not. So if something else that is greater than this vanishes as r goes to infinity, that's fine. So we just make use of this fact. I have sine theta, and its value is maximum at theta equals 1/2 pi. So if I just draw a straight line from the origin, that parameterization is just a 2 theta over pi. If I substitute theta equals a pi over 2, then it is just 1, as we have expected. And again, this is a sine function, and the integral over theta is running from 0 to pi. This is symmetric from 0 to 1/2 pi and from 1/2 pi to pi. So it is exactly the same as double of the same integral from 0 to 1/2 pi. Okay? And then if we consider this part, sine theta is always greater than 2 theta over pi. So sine theta is always greater than 2 theta over pi. If I take the exponential and put negative sign and exponential, then this exponential minus sine theta is always less than exponential minus 2 theta over pi. Alright, so this integral is less or equal than this integral. Let us see. If I take the integral, it is possible to integrate over theta. So the answer is, I have inverse 2r, so 2 cancels. I have r and t in the denominator. I have pi in the numerator. If I substitute pi over 2, it cancels. And I have exponential minus rt, right? And if I substitute 0, then this argument becomes 1. So this is actually pi over rt, 1 minus exponential minus rt. Okay. If time is positive, this guy becomes very big, so it goes to minus infinity. So we cannot control the size of this integral. We do not know the value of that integral. But if t is positive, this overall factor is just approaching 1, and this value approaches 0. Because this 0 is an upper bound of absolute value of this integral, if t is positive, that integral must vanish. Therefore, this integral equals 0 if t equals positive. Okay? If time is positive, this integral is 0. So that means this whole contour integral is the same as the integral from minus infinity to infinity. And what is that value? That was 1. The contour integral along the C minus was 1, regardless of the fact whether t is positive or negative. But only when t is positive, this semicircle integral vanishes. Therefore, I can make use of this fact. This value 1 is exactly the same as the integral along the real axis. Okay? So that is 1. So I'd like to show that the integral from minus infinity to infinity becomes 0 when t is negative. So that is our next step. So that's what I have already explained. If t is negative, what happens? If t is negative, I cannot make use of this relation to find whether this is a positive, whether this integral vanishes or not, because the upper bound runs to infinity. So why don't we choose the upper half plane in case t is negative? When t is negative, we can make use of exactly the same method, and we will find that this integral becomes RT sine theta instead of minus RT sine theta. Okay? Here, minus RT sine theta. For positive t, we made use of this kind of inequality to find that the absolute value of this integral vanishes, therefore this value vanishes. But in case if t is negative, we follow the similar method to find that this integral vanishes on the upper half plane. Upper half plane. So let us recall the fact that contour integral along the C plus contour was what? Was exactly 0 because there was nothing. There is no residue in it. Therefore, this integral is 0 and integral along the C plus is 0 when t is negative. If t equals negative, integral on the upper semicircle is exactly the 0 and the whole integral is 0. Therefore, if t is negative, integral from minus infinity to infinity along the real axis of this integral is vanishing. So in summary, if t equals 0, t is positive, that integral along the real axis can be interpreted to be the integral along the lower half plane. And actually in that case, if t is positive, this integral vanishes and this contour integral, which is the same as 1, is the same as the integral from along the real axis. Therefore, this value is 1 when t is positive. If t is negative, we can close the contour along the upper half plane, and the contour integral along the upper half plane, this upper semicircle, is exactly 0. And in addition, if t is negative, the integral along this semicircle on the upper half plane exactly vanishes. Therefore, the integral along the real axis from minus infinity to infinity vanishes if t is negative. Therefore, we have shown that this integral is exactly the same as the theta function. That's it.